Hello, good morning, my dear NEET 2025 warriors. It's time to start the most demanded session, which is the mechanical properties of solids, a detailed one shot with you. Yes, your captain Shreyas is back. And like it happened in JEE this year, where NTA's favorite topic was mechanical properties of solids and fluids, sometimes they used to ask around 3 to 5 questions just from this particular unit. And those traditional favorite topics of electromagnetic induction were never asked. So you never know what's going to happen, and NTA is all set to break all the rules and all their favoritism towards certain topics. So it's our responsibility now to study each and every topic in detail so that no matter what question they ask, we are prepared. All right, so let's begin with the class. And all the warrior pandus, whistle, podu, WP should be trending in the chat box. This is your Captain Shreyas, and I have been training kids for more than 13 years now. And countless students are right now in their prestigious colleges, and many of them have even graduated from them and doing extremely well in life. And I take immense pride in having nurtured them, trained them, and guided them through this important phase of their life, which is their 11th and 12th standard. And all of you are right now in this particular phase, and I really hope that this year is your year and this is your last NEET that you are going to write. Okay, so let's begin with the class. Thank you for liking. If you have not yet liked, please like this session and also subscribe to the #1 NEET English channel. And we are about to be 200K. Krishna, I'm very good. Nice to see you back. Dinesh, Disha, Achu, Evening Star, morning, good morning. Rajkumar, welcome. Hi Sukanya, good morning, my dear students. Good morning. Wow, nice to see all the fire in the chat box. Hi Bharti, I hope you are doing great, and I'm doing great too. And yes, all the important videos are coming in on the channel for your registration, for your counseling, for your preparation, for the strategy, for all the detailed classes, problem solving. Everything is happening on the channel. So you need to stay subscribed because now the game is going to get more intense. Right now, just last month I was very busy with the JEE preparation, and obviously there is a board examination going on in another state, so I'm busy with that too. So as and when things permit, I am coming and making sure that I'm delivering big classes, but otherwise I'm making sure at least I am in touch with you with all the important guidelines or even the strategies. All right, so let's begin, my dear students. Let's begin. Now this particular chapter, mechanical properties of solids, first starts with the idea of something called as a rigid body, plastic body, and a elastic body. So let's understand the difference between these three. What is the meaning of a rigid body? What is the meaning of a rigid body? A rigid body is a body which does not deform, which doesn't deform, whether it is its shape or basically its size. It doesn't change upon the action of upon the action of external forces, upon the action of external forces. There is no such body which is rigid, because something or the other will move, will shake, will turn, will bend, it will change its size, contract, something will happen. But yeah, stones, marbles, metals usually are considered to be rigid because it's very difficult to change its shape and size. I mean, it is not noticeable to the eye, right? This wall which is there, it's almost like rigid. Yeah, it deforms a little bit under the microscope, but for the naked eye, it is hardly noticeable. That is the meaning of rigid body. The next thing is a body which is basically elastic. Elastic body. What is the meaning of elastic body? An elastic body will regain regain its original regain its original shape and size, shape and size when left, when left, when left, okay, after being deformed, when left after being deformed. There are many examples of this, like the tail of a dog. You have seen a dog wagging its tail. The tail will bend if you pull it, but you leave it, it comes back to its original shape and size. And there are proverbs on that. Your behavior is just like the tail of a dog, meaning no matter how many times we try to change you, you again come back to your original values and your original thinking. So, elastic, a spring, you pull it, leave it, comes back. You compress it, leave it, it comes back. A rubber band, you pull it, leave it, it comes back, right? So these are all elastic bodies, meaning you deform it, it gets deformed, it's not rigid, but when you leave it, it comes back. That is the meaning of elastic body. Yes, Achu, if you're starting from now, you can definitely get it. But I want everyone to be sincere, be motivated, and be consistent and practice a lot. Trust me, you will conquer it. Okay? It's not a distant dream. We still have a good around 3 months time. We can definitely do it. Okay? Cool. My voice is breaking, is it? I don't know why. Let me just try some other mic. Hold on. Is it fine now? Just check. Bharti, is that fine? Hi, Sukanya. Thank you for all the love. Okay. Yes. Just see if it is fine now. Now is it fine? Okay. Krishna says it is fine. Yeah. Sir, will important topic enough for physics by PYQs? No, Achu. You have to do everything. There is nothing like important. Somebody will say this is important, that is not important. Now is not the time for that. Please study everything. You have time. Okay. Try to do everything. All right. Now, the next type of body that you have is basically called as plastic body. Plastic body. Now, a plastic body basically gets permanently deformed, gets permanently deformed, deformed, and and has no restoring effect, and has no restoring effect, meaning that, let's say for example, clay, you might have played with clay as young kids, and you would have made different clay models and shapes and sizes of different sizes. So when you press that clay, it will get deformed permanently. You pull that clay, that's it, it's done. Or even cheese, which is there on the pizza or in the burgers, you pull that, leave it, it stays there. Chewing gum, the chewing gum which is there, you pull it, leave it, it is deformed forever. So that is elastic behavior. Okay, where the body once deformed, it is permanently deformed. Okay, and there is no sense of restoration. Restoration means you are bringing it back, just like an elastic body which has restoring effect, where it tries to come back. There is no tendency to come back. It's like telling a student, hey, study. He's continuously studying. He's not even going to play. Hey, play, come on, you should play now. Okay, fine, I will play. So the student just starts playing. He does not study at all. So that is like plasticky behavior. It does whatever you tell it to do. Elastic is, you tell him something, he will do as long as you're watching. But once you stop watching, the kid comes back to his original life. Rigid means no matter what you tell, no matter what you tell to the kid will not listen. It's like talking to a wall. No use of talking. That is the meaning of rigid. I hope these three differences are absolutely clear. Okay? These three differences are absolutely clear. Now, we talk about basically elastic bodies in this particular chapter. So, imagine there is some kind of an elastic body, there is some kind of an elastic body which on the application of, oops, which on the application of an external deforming external deforming force or forces, it gets deformed. It definitely will get deformed, maybe the size will change, or maybe the shape will change, something will happen. So there is some kind of deformation which occurs. There is some kind of deformation which occurs. Either the size will change, or the shape will change, or both will change, something like that. So we basically focus on these three aspects of an elastic body. There will be some material aspect, there will be some nature of the material compound aspect, there is some external aspect, and then some effect will be seen, which is the deformation aspect. So these three effects, these three things is what we are going to see in this particular chapter. Now, this cause, which is an external force which deforms the body, has a term associated with it, and it is basically called as stress. The symbol for that usually is sigma. Stress is basically the intensity of that deforming force, intensity of that particular force which is going to cause that deformation. The stress is that intensity of that force. Deformation is often measured by a quantity called as strain, is often measured by a quantity called as a strain, and this strain has a symbol of epsilon, and strain is basically the relative deformation which occurs. It is a dimensionless quantity. Strain, it is having no dimensions at all, no units at all, whereas stress, you will see, it has the unit of Newton per meter square, or basically Pascal. Newton per meter square, or basically Pascal, same like pressure, because it is the intensity of the force. How much force is there per meter square of that inch of that area? So it is the intensity, how intense that force is concentrated in that area. So newtons per meter square, which is also known as Pascal. Okay, right? And lastly, the property of that elastic body, the material property, is called as the modulus of that body. Now there are different symbols depending on the deformation, we'll come to it. Modulus, which is basically the material property, depends from material to material. Like stone will have different modulus, steel will have different modulus, plastic, wood, etc. depends, like coefficient of friction, or density, or viscosity coefficient. All these are material characteristics, and the unit of this is also going to be Newton per meter square, or basically pascals. This is also a quantity with dimensions and with units, and this has the same unit and dimensions like stress. The symbol for that will change depending on the deformations which occur, but for now just remember it is a material characteristic. No matter what the stress, no matter what the strain, this is a character associated with whether it is aluminum, steel, plastic, stone, tar, etc. Stress is the cause of that deformation. It causes that deformation, and how intense is the deforming force is measured by sigma, which is stress, and how much deformation occurred relatively, because it is a relative measurement, hence it will be a ratio. You can guess it, it will be without any units, without any dimension, and that is why it is having no dimensions inside here. It is having the symbol epsilon. Is this absolutely clear? Is this absolutely clear? Yes. Nice flow chart, right? Yes, don't worry, you are going to get everything. Hi, Dr. Tanuja. Yeah, CBSE session Sai, they are already started on the Vedantu J English channel, like I mentioned a day before or something, that we will be conducting the CBSE classes on one channel, because I don't want to conduct the same class on two things. Unnecessary students are confused. And anyways, you know, we have the Vedantu J English channel, the same teachers are there for your physics and chemistry. So you're going to have the chemistry, physics classes over there. Maths, if you have, you can watch it. Else, don't worry. And apart from that, biology classes will happen on this channel only when the biology board exams will come. Okay, clear? Now, Like I said, the modulus has different symbols depending on the deformation type. So what are those deformations that I'm talking about? So what happens is, when you, for example, say you have, let's say a building, or let's say a bridge, or let's say a column, anything. Let's say this is a particular bridge, okay, and this is, let's say, a column of that particular bridge. Maybe some vehicle is going onto it, so there is a force here. Maybe sea waves are crashing onto it, that's why there is a force here. Maybe the wind is blowing, that's why there is a force here. Another truck is going, that's why there is a force here. Maybe some wire is pulling that particular thing, so maybe there is another force here. So because of all of these things, this particular bridge might deform. It might probably look like this. It might look like this. I'm just chumma saying or drawing it. Okay, I'm just drawing it like this. This is highly exaggerated, guys. This is just to show this is the deformed bridge. This is how it has been deformed. Now you can see it is a very complex analysis. So to find the deformation, this is very important. To find to to find to find the the deformation of bodies is usually complex is usually complex and calculative under the action of under the action of multiple forces multiple forces under the action of multiple forces. But what we do is very important. But in our NEET syllabus, JEE syllabus, CBSE syllabus, basically our 11th and 12th grade, we study deformation of, or rather we will say we study elementary, elementary, like you have elementary, then secondary, then higher secondary, then higher education, like that. Elementary school means basic, elementary, elementary, or basically the very fundamental deformation, basic deformation of of standard standard bodies standard bodies. Now, which are those standard bodies that I'm talking about? Usually what you will be studying is basically rods, cubes, okay, box, these things. Okay, generally you will be studying these kind of things: rods, cubes, boxes, cylinder, etc. Rod and cylinder, most likely the same thing. A rod is like a cylindrical body. You are pulling it, it deforms, it elongates, it compresses. So these kind of things is what we study in our NEET syllabus, not the complex deformations. Okay, so let's take those standard basic things, usually like the cubes, rods, cylinders, etc. So what are those three deformations that we are going to study? Observe this very, very carefully. Observe this very carefully. Now, if you take, let's say, a cubical object, let's say you take a cubical object or a rod-like object, something like this, then same thing over here, same thing over here. And what you do is basically you are pulling it, or let's say you are pushing it. Let's say you are pulling it, or let's say you are pushing it. So basically it will look something like this. I am pulling it, or let's say I am pushing it. I am compressing it, or I am stretching it. In such a case, what happens is that body might become like this. It has become longer. Here, it would have become shorter. Here, it would have become shorter. I am applying the force. Can you see? I'm applying the force perpendicular. These forces are basically perpendicular. These forces are perpendicular to the face. When the force is basically perpendicular to the face, and you are saying that there is either elongation either there is elongation or basically compression. Elongation or basically compression. Such kind of deformation is basically called as elongation, long. So longitudinal deformation. This is called as longitudinal deformation. Is this absolutely clear? Example, there is a rod hanging from the ceiling, you are hanging from the rod, longitudinal deformation. There is a column on which the bridge is supported. The column gets pressed from the vehicles going on the top of it, that is compression. Again, the length is affected, so the forces are perpendicular to the face on which the body is. So the force is perpendicular to the face. Again, it is longitudinal deformation. I press this pen, I pull this pen, longitudinal deformation. Is this absolutely clear? Very good. Next, what I do is that I am going to apply the force parallel to the face, something like this. I'm going to apply the forces parallel to the faces. So what happens is that particular body might become like this. The body might just become like this. Observe, the body has got bent, it has got deformed. Such kind of deformation where the force is basically parallel to that face or that surface, parallel to that particular face, and you will see that the object is going to bend. It is going to bend. All right, then such a deformation is basically called as shear deformation. It is called shearing. It is called shearing. I'll give you some examples. Don't worry. I have a big book over here. It is NCERT Tejas book from Vedantu. All right, big book with lots of problems based out of NCERT, pure NCERT questions, but for NEET. Okay, so what I do is I apply a force onto it like this or like this. Can you see? Can you see my force is parallel, not perpendicular? This is perpendicular. This is parallel. If I apply the force parallel, see how it is bending? Can you see the shape which was straight? It has gone like this. See, I apply the force like this. It has gone like that. The layers slide over each other. The force is parallel to the face, and that's what happens. It gets sheared. Shear. When a woodcutter takes an axe and cuts the wood and he chops the tree, the force of that axe's blade is parallel to the surface which is being chopped. Okay, once that cut is made, the force is parallel to that surface, and that force will slide the layers, and that is also shear. You can visualize that is also going to be shear deformation. The last one, usually these two are associated with solids. Usually you will talk about these kind of deformation for solids. This is for solids. But for fluids, when I say fluids, it means both. It means gas and liquid. Both these states, gas and liquid. And then what you do is you are applying some pressure, maybe from like this. Pressure is always applied from everywhere. It is not just from one side. So there is some pressure which has been applied onto it, and because of which maybe this particular body compresses, something like this, because of that pressure. So the application of the pressure, so the pressure changes are there. Pressure changes are there on the body, which directly affects the volume and the density. Volume and the density. Such kind of deformation is called as bulk deformation. Such kind of deformation is basically then called as bulk deformation. Example, you take a water balloon, you apply pressure, that water balloon will compress. Or you take some solid inside a liquid, the liquid pressure will try to compress it. Or you take some gas, you take it on the at high altitude, because pressure is less, it will expand. So changes in the pressure will cause contraction or expansion, increase in the density or decrease in the density, such thing is called as bulk deformation, usually associated with figureless, shapeless bodies, meaning fluids, that is liquids and gases. Is this absolutely clear, everyone? These three, are you able to visualize it? Awesome. Now, let's see all these things: stress, modulus, deformation, for all the three kinds of things, so deformation, longitudinal, shear, and bulk, one by one at a time. Then you will get a clear-cut idea. So let's talk about longitudinal deformation over here. Longitudinal deformation, longitudinal deformation, longitudinal deformation. So we have, let's say, a rod-like object or a cube or a cuboid or a cylinder, whatever you want to call it. And let's say right now it is in its natural state. So this is L. So this is its natural shape and size. This is its original shape and size. Let's say it has, let's say it has, okay, let's say it has some area of cross section which is A. Now what happens is elongate it, you elongate it. So maybe you have applied some force, or you can even compress it, no issues at all. And because of which the rod becomes slightly longer, something like this. Second. Okay. So you have applied some force like this. This force obviously is perpendicular. Obviously, you have to support the rod. If you don't support the rod, then it will fly off. So you have to always pull it from both sides, or else the rod won't stay at rest. And because of which you can clearly see that there is some elongation over here. And that elongation is basically X. It could be also compression. So X, I will say, is basically the deformation. X is basically the deformation. It could be positive or negative. When it is positive, what it means? When it is positive, what it means? It has increased in length. When it is negative, what it means? It has decreased in length. Is that right? Very good. Yeah. Questions are also going to be there. Yes, Sukanya. Once let me complete the basic theory. Obviously, I'll come to the questions. I don't want to miss any theory part, because there are some students, in fact, many students who want to learn from the basics. So questions will also be there. Don't worry. Okay. So now the logic goes like this. The logic goes like this, that the stress calculation, which is the longitudinal stress. Sigma is the symbol for stress. The longitudinal stress is the force, which is that perpendicular force per unit area. This particular perpendicular force, which is there per unit area. Remember, I had told you stress is how intense, how concentrated that force is, measured in Newton per meter square. Okay, so that is why Newton, and over here meter square. That is the longitudinal stress calculation. All right. So that is one thing. Then you have the strain calculation. So the longitudinal strain is given by how much is that deformation relative to the original length. So the deformation is this much, the original length is this much. So this is relative. I hope this is absolutely clear. Okay. So this is basically x by L. I hope this is absolutely clear. Now, I do not prefer delta x by L. I'll tell you why. Because in some problems which involves derivatives, it can lead to a lot of confusion. So instead, some people also use small l by capital L, which can also cause more confusion. I would suggest you to use x by L symbol. You will see in some problems how it is going to benefit. Yeah, I hope this is absolutely clear. Now comes the final part, where we are going to use something called as the Hooke's law. And Hooke's law basically for elastic bodies says that our stress which is there, the stress which is there, the stress which is there, the stress which is there is directly proportional to the strain, is directly proportional to the strain, and this happens till a certain limit which is also called as the proportional limit. Proportional limit, proportional limit, there is a limit till which the applied stress proportionately increases with the strain linearly. Otherwise it can be non-linear, quadratic, square root, cubic, sine, whatever. There is only certain times this law, in fact many times it is valid, but there can be some exceptions also. And then I can just say the constant of proportionality, so sigma is divided by our strain, sigma is divided by our strain, and that constant of proportionality for longitudinal deformation is y, which is then called as Young's modulus, which is then called as Young's modulus. Young's modulus. So this is the main formula, my dear warriors. This is the main formula, my dear warriors. Stress by strain is Young's modulus. As you can see, this is dimensionless. This is Newton per meter square. So if this has no dimension, no unit, correct? And this has Newton per meter square, Young's modulus will have the same unit or even the dimensions as the stress. They both are in the numerator with same units and dimensions. This guy has no dimensions. That's the reason why in this particular slide, I told you, yeah, modulus of elasticity has the same unit or dimension as that of stress. That is the logic behind it. This is always a relative quantity. It's like a ratio. So no units, no dimensions. Is this point absolutely clear till this point? Examples of Young's modulus. Example of Young's modulus. Example, Young's modulus of steel is of the order of approximately 2 into 10 to the power 11 Newton per meter square. That is huge. That is huge. Okay. But maybe for plastic, it will be less, maybe 10 to the power 9, 10 to the power 8, like that. So if one guy has more Young's modulus, this is very important. If Young's modulus is higher, if Young's modulus is higher, it means that it is difficult to deform. Difficult to deform. It is difficult to deform it. And when Young's modulus is infinity, then it means it is perfectly rigid. There is complete rigidity in it. And if by chance Young's modulus is zero, if Young's modulus is zero, meaning there will be no stress for no matter what strain you apply, there will be no force required to stretch it. I mean, it will just stay there. It will have no stress at all. It will just deform. There will be no restoring forces to bring it back. Such a thing is then going to be a plastic body. Such a thing is then said to be plastic in nature. Okay, so more Young's modulus, very tough to deform it, very easily deformable. It is plastic. I hope this is absolutely clear. Okay. Meena, we are already doing sessions for boards on the Vedantu J English channel. So please start watching it. Okay, a lot of sessions are lined up. Okay, you will probably see it in the recorded videos. So it's going to come up like this with this kind of thumbnail: CBSE 2025, chemistry, physics, maths, etc. So every day lectures are being conducted. Plus during individual exams, marathons, mock tests, sure shot, most probable questions, problem practice, everything will be continued. Okay, I hope this is clear. All right, Emperor, I'll definitely try, my dear. Okay, okay. Now that was Young's modulus. Next deformation. Next deformation. Before we go, let's do a problem on this so that you guys understand this properly. Example. Example. Let's say there is a wire. Let's say there is a wire. There is a wire, and maybe it is made of some metal. There is a metallic wire whose Young's modulus is given to be 5 into 10 to the power 10. 5 into 10 to the power 10 Newton per meter square. It has been held from the roof like this. And what happens is there is a elephant over here. There is an elephant over here which is hanging. So let's say this is our elephant. Okay, beautiful elephant, guys. Okay, and the mass of that elephant, let's say the mass of the elephant is 2000 kg. 2000 kg. Example, mass of the elephant is how much? 2000 kg. Okay, it is also known to us that this particular cross-sectional area, this particular cross-sectional area is, let's say, 10 centimeter square. 10 centimeter square, small cross-sectional area. So this is also given to me, and the length of the wire is, let's say, 10 meters. 10 meters is probably the height of a room or two rooms, okay, or two-story building. Wow, thank you Pratibha and Krishna for giving all those elephants for free. Okay, Rajkumar, no, no, no. The elephant is not committing suicide. No, no, no. It's not done anything. Don't worry. Okay, it's chilling out. It's like hanging out. They say, I'm hanging out with my friends. So this elephant is just hanging, bro. Okay, don't put dark humor in it. Okay, all right. So anyways, and don't worry, elephants don't have to give any kind of exams, right? So it's pretty chill. Elephants just have to eat sugarcane and just roam around and just blow their trumpet. That's all. I mean, really cool, right? Okay, so the question is, can we find how much extension is there? Can we find how much extension is there in that particular rope or that whatever rod? All right, we can do it. It's not that difficult. So I will say that we know Young's modulus, area, length, and the mass. So from this, using our formula, which is basically Young's modulus is stress by strain, I think we can find out the elongation. What is the value of stress? It is the force per unit area. Strain is the extension per unit length. But I want to find x. So bring x on the top, bring x value on the top. This force and this area is going to be as it is. This length is going to go on the top. Young's modulus is just going to come over here. Perfect. Now let's see, do I know everything? So what is this force going to come to? This force is going to come because of the weight of the elephant. So instead of the force, it will be the of the elephant, weight of the elephant multiplied by the length of that particular wire on which it is chilling out or hanging out. This A is that area of that particular cross section, and basically Young's modulus, so that is the of modulus of that particular metal. I think all these values are given to me. All these values are given to me. So let's substitute and see what do we get. Weight of the elephant is mg. Do not forget, it will be basically mg. So mass is basically 2000 into g. G is basically 10. That's your first term. Length of the wire is 10 meters. So multiply it by 10. Okay, that is also taken care of. Area of the cross section is 10 centimeter square. A centimeter is 10 to the power negative 2. Centimeter is 10 to the power negative 2. So square will be raised to negative 4. Squared of a centimeter, 10 raised to minus 2 square. All right, great. Next important thing, modulus of that metal. Modulus of that metal is nothing but given to be 5 into 10 to the power, what is it? 10. Okay, perfect. Let's see what and all things will get cancelled over here, and accordingly we will adjust. Well, this zero just got cancelled. We have 1, 2, 3, 4. 1, 2, 3, 4 zeros. This 4 zeros will cancel. This will become 10 to the power 6. Minus 4 and plus 6. This will completely go off. This will then become 10 to the power 2. 10 to the power 2 will go on the top and it will become 10 to the power negative 2. Is that right? So what am I left with? What am I left with? See what and all happened. This 0 cancelled. 1, 2, 3, 4 zeros, and 4 zeros becomes 10 to the power 6. Minus 4 and plus 6 becomes plus 2, goes on the top as minus 2. So I'm left with 2 by 5 into 10 to the power minus 2, but I don't want it like that. 2 by 5 is nothing but 2 by 5. Come on, my dear warriors. Yeah, it is going to be 0.4. So it is going to be 0.4. So it is going to be 0.4 into 10 to the power minus 2. But this is in meters. I don't want it in meters maybe now. I will probably write it as 4 into 10 to the power minus 3 meters, which is then 4 millimeters. That is our answer. So 4 millimeters is our answer, my dear warriors. It's this small. Small the wire has extended. This small the wire has extended. What an answer. Amazing, isn't it? Cool. Let's do next question. Let's do next question on Young's modulus. Now, in this particular question, what's going to happen is the rod is having multiple cross sections. The rod is having multiple cross sections. Something like this. Observe carefully. Like this and like this. Versus like this and like this. And let's draw over here like this and like this. Okay. So this is a wall on which it has been supported. This is scenario 1. This is scenario 2. Okay. Both are of the same material. Let's assume same material in both the cases. Same material. If material is same, that means the modulus of elasticity is the same. It's just that the area of cross section is different. That's all. Now, what is happening over here is basically they are clubbed together and you are pulling it with a common force. Yes, you are pulling it with one force, and here also you are pulling it with one force. All right. So let's draw it over here. Draw it over here, F. So what do we have to essentially do? Essentially, compare number one, the stress. Number two, the tensions, the tensions, the tensions in both of them of elongation. Number three, the strains, the strains, and number four, the elongation, the actual elongation. That is what you have to do. This is also length L, this is also length L. Obviously, this is L and this is also L. So I'll just shade it for you just in case. Yes, this is the rod. This is the rod. This is the rod. Okay, so basically this is L. All right, so this is the question, my dear students. Let's see if you guys can figure this out. You have to compare the stress, strain, elongation, tensions, everything in both the scenarios. Let's go part by part. Let's go step by step. Let's see this diagram first, maybe then this diagram so that we get an idea. Okay, Jan session result will come by tomorrow. Okay, Sivan, yesterday only they have uh, declared the final answer key. Oh, great, Sanjay. You have been watching my old thermodynamics classes. They are still up to this. I mean, Mark, I mean, you don't have to worry about new classes or old classes. They are the finest lectures and you will obviously understand everything. All right, cool. So let's see one by one. In this particular problem, what I would say is that if you draw the free body diagram of this small rod versus this big rod, what you will notice is that because both of them are at rest, if there is a force F here, there will be the same force F over here, and by Newton's third law, this force will also be F, and this force will also be F. This force will also be F. That means the force throughout is the same, and that was one of the question, the tensions. So this force itself is the tension. So the tension is same. So the tension is going to be the same in both the rods. Okay, so the tension is going to be the same in both the rods. Perfect. What about the stress? Now we know stress is basically that particular tension which is there per unit area of the face. The one which has more area will have less stress. The one which has less area will have more stress. So over here, this has bigger area, this has smaller area. So therefore, the stress, if I may label them, let's say I label this as number 1, let's say I label this as number 2. This is labeled 1, this is labeled 2. So in this case, I can clearly see stress 1 is more than stress labeled 2. This is more stress because less area. This has less stress because area is more. Less area, more stress, more area, less stress. Is that absolutely clear, my dear students? All right. Now, Young's modulus is the same because same material. That means Y is basically the same for all of them. It is a materialistic property. Next important thing is the strain. We know we know that Young's modulus is stress by strain. Y is same for both of them. So therefore, stress is directly proportional to strain. The one which has more stress should also have more strain. Hence, because stress 1 is more than stress 2, therefore, epsilon 1 will be more than epsilon 2. Epsilon strain 1 will be more than strain labeled 2. Is this clear, my dear students? All right, great. The guidance session will be conducted this week, Joy and Roy. I know you guys have filled the forms, so this week the counselings will begin. Okay, we have started allocating the slots. Slowly you will get the calls. Now, strain is also elongation by original length. Elongation by original length. L will cancel, so x1 will be more than x2. So we have completed all the 4 answers for this particular diagram. Stress 1 more than stress 2, tensions are equal, strain 1 more than strain 2, elongation 1 more than elongation 2. Is this absolutely clear, my dear students? This first part, everybody with me? Give me a thumbs up if you understood. We have done all the steps so that you guys understand it. Great. Combined Young's modulus also we can do. We can do those kind of questions. Just 1 second. We'll first do this problem and then we'll come to that also. Series, parallel, you have to find the combined Young's modulus, how to do those questions. Here, how will that force get distributed? Well, that force will be partially applicable here and partially applicable here also. So this will be basically F1. This will be basically F2. I do not know which one will be more, which one will be less as of now. As of now. But I know one thing for sure. Once I pull it, this particular edge will come over here. So both of them will move like this by the same amount. So that is basically the elongation, and that elongation is the same. This will be x1, this will be x2. x1 will be equal to x2. Is this absolutely clear? Here elongation is the same. Elongation is the same. Oh, that also means x1 by L will be x2 by L. Therefore, what is this? This is strain 1 and this is strain 2. Strain 1 equals to strain 2. Is this also clear, my dear students? Elongation will be same, so strain will also be the same. So we have done the part of strain and elongation. Now we'll do the first 2 parts. See, some problems you have to go like this, some problems you have to go like this. That is what you are learning when you see problems. It's not like you don't know the formulas, but how to approach them, you have to think differently. The moment I saw the forces, I knew I cannot start from forces which I did over here, because here forces was my starting point of the problem. But here I do not know anything, so I have to think a little bit differently. Now what I will do, okay, strain is the same. Young's modulus formula. Oh, Young's modulus is stress by strain. Strain is same, Young's modulus is same. If that is the case, what can you tell? Therefore, stress A1 will be equal to stress 2, because both of them are going to be the same for this rod and this rod. So hence stresses are also going to be equal. But what is stress? It is nothing but force by area. Force by area. F1 by A1 will be F2 by A2. Now who is more, who is less? We can always see this. F1 by F2 will be A1 by A2. We all know A1 is less, A2 is more. Since A1 is less than A2, therefore F1 will be also less than F2. This ratio will be less than 1. So this guy has less force, this guy has more force. So we have compared that as well. So we have completed all the 4 parts. Is this absolutely clear, my dear students? Okay. So what happened in the first case is that because the rods were connected one after the other, whatever force was applied on this end was transmitted onto the other end, and whatever force this phase applies on this, same force second applies on one because of Newton's third law, action reaction. And whatever force is applied on this face must be applied on this face because the entire rod is at rest. So the forces should be balanced by Newton's first law. So that is why F is same. That means tension throughout the rod system is the same. So my starting point was the force. Whereas over here, I saw the rods were pulled in parallel, so their extensions were the same. That is the reason why my starting point was extension from that strain and from that stress and from that the force. Here the process was exactly opposite. The process was exactly opposite. Yes, the rods are connected. Yes, yes, yes. Yes, Jovan. Rods in series and parallel, they are always connected. Thank you, Krishna. Thank you, Krishna. Okay, great. Moving on, moving on, moving on. Now, there could be certain questions where you have to find effective Young's modulus or effective modulus of elasticity for rods in combination and stuff like that. So, what do you do in such cases? Say, for example, you have been given one rod over here and another rod over here. Okay, this rod has Young's modulus y, this has Young's modulus, let's say 4y, this has, let's say, length of L, and let's say this has a length of 2L. Can you find the Young's modulus effectively? Can you find the Young's modulus effectively? The answer is very straightforward. Let's do one thing. Let's replace this combined rod, or rather two rods, with one combined rod. Let's replace it with one singular rod, and it will be something like this. It will be something like this, and the Young's modulus will be y effective, and number one, the length will be then 3L. Obviously, it will be having complete length of 3L. Area of cross section will be the same because you have to replace both these rods with one singular rod. Okay, that's the catch. Now, what will happen is, see, each rod will expand when you apply a force from here, when you pull this from here, or when you pull this from here, there will be some deformation. Let's say this effective rod has a deformation X. What will happen over here in this case, when the rods are in series, go back to this problem. When the rods are in series, what is same? The force gets transmitted. The tension is the same throughout all the cross sections of the rod. So therefore, can I say the pulling force, or rather the tension or basically the pull is the same. The tension or the pull is basically the same, but what is generally different? What is generally different is their elongations. Their elongations are generally the different things. So, but the deformation, or basically the elongations elongations may be different, may be different, may be different. And each rod might have elongations. Let's say one is having x1, the other guy is having x2. One thing I know, that if this guy extends by 1 centimeter, this guy extends by 3 centimeters, this will push it by 1 centimeter. This rod will extend by 3 centimeters. So this rod will move ahead because this rod has moved by 1 centimeter. So the total elongation x, so what will happen? The total elongation x which is there, that will be x1 plus x2. That will be basically x1 plus x2. Is this absolutely clear, my dear students? X will be equal to x1 plus x2. Absolutely fine till this point? Great. Now, in general, what happens? In general, we all know Young's modulus is stress by strain. Stress is force by unit area. Strain is elongation per unit length. Therefore, X will be FL by AY in general. So why not write instead of X force into the length, length is basically 3L divided by area of cross section into effective Young's modulus will be equal to X1 for this guy. The force is the same, the length is basically L divided by A into Y plus the force is the same, the length for this rod is basically 2L divided by A into Young's modulus, which is basically 4 times of Y. So many things to cancel. So many things. F, 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 L, 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 A, and A. Correct? This 2 with this 4 becomes 2 over here. So what am I left with? Check this out. 3 by effective Young's modulus. Is that right, my dear students? Is equal to, this is just going to be 1 by Y over here plus this is just having 2Y over here. 1 plus half is 3 by 2. So this will be 3 by 2 times of Y and this will be 3 by Y effective. 3 and 3, of course, again they will cancel over here. So therefore, what do I get my Young's modulus effectively as? So the effective Young's modulus will be just 2Y. Effective Young's modulus will be 2Y. Got it? So Jovan, that's how we found out effective Young's modulus. That's how we have done it. So the crux of the problem was to identify, from this problem we got an idea. So that's why you have to always increase the level of the problem. One problem's solution gives you the hint or the starting step for the next problem. We understood the tension is the same. So that is the reason why I started my problem by saying the tension is the same but the elongations are different. And I know this rod will extend, this rod will also extend and it will push this rod. So the total elongation, the amount by which this phase moves, will be basically this guy's extension plus this guy's extension. And that was my beginning, I would say, equation. And X in general, I found out from our original formula of Young's modulus. So I got in general expression of X. I substituted X for 3 different rods. This X was for this was for this was for this. Individual lengths, individual moduli. Got it? Clear? Absolutely? Perfect, my dear students. Perfect. Now that we have understood this particular problem, let's go ahead. Let's go ahead to another amazing question. Another amazing question which can come in your examination. Now, this is very nice because it is going to involve little bit of complexity, but that is fine. Here what happens is there is a rod which is having, let's say, certain length. It is suspended from the roof. It has a certain cross-sectional area. It has a certain Young's modulus and density. This is modulus and this is basically your density. Find the extension of the rod. Find the extension of that hanging rod due to its own weight. There is no extra weight due to its own weight. Due to its own weight, it is going to come down. Crazy problem this is. How do I solve this? Now, many students are going to think, okay, in order to solve this particular problem, sir, the total weight of the rod I know. So the weight I will take divided by the area, I will get stress. Stress I know, modulus I know, I can find the elongation. But that approach is definitely not correct. The reason for that, no issues dreams, you can start watching from now. If you have missed something, you can always rewind back even in the live class. The problem is the stress isn't constant throughout the rod. Just think about a rod and it is not massless. It has its own weight hanging from the ceiling. I have a feeling the most responsibility is there with the topmost edge of the rod because it has to balance the entire weight of the rod hanging below. whereas the end of the rod below has nothing to pull, so it has the least responsibility to support anything. So, be it a point here or here or here or here, the tensions are not the same because this guy is least responsible, has nothing to pull. This has something more to pull. It has to balance more weight. This has to balance the most weight. So the tensions will change, stress will change, strain will change, elongation will change, section by section by section. So that means the first step of the problem is to figure out how much tension is there at any random point, let's say at X. Is this absolutely clear, this concept? The tension will not be the same. So that's the reason why it is not a simple problem. See, they say that an intelligent or a smart person understands when the problem is difficult. But if you don't know anything or if you have not studied, then you will feel that oh, every problem is easy. So whenever students come out of the exam hall and we ask, how was the paper? And some students say, oh, it was very easy. It was very easy because you felt everything was easy because you have not studied anything. So for you, it doesn't matter whether you score high or score low. So when you appreciate why this problem is hard, that's when you're truly understanding it. So don't get bothered when you feel that the problem is hard. In fact, you should feel happy. You are feeling that the problem is hard because you are trying and because your brain knows why it is hard. So it's actually a good thing. It's actually a good thing. Okay, so let's start by analyzing what will be the, this is not needed. What will be the tension at any random point? So what I'm going to do is I'm going to just take a random place over here, random place, random cross section over here. Let's say I call this as X. Let's say I call this as X. And at this particular place, there will be some kind of tension. There will be some kind of tension. And that tension will have to balance the entire weight of the rod hanging below. That is the most important thing. That is very important. So this particular tension, the tension changes, the tension changes with height, in this case X, and this tension should balance what? The weight, the weight hanging below, the weight hanging below. Now the weight hanging below will be the mass which is hanging below multiplied by g. Now how much mass is hanging below? That is very interesting. Just let's say for the sake of it, the total mass of the rod is m. That is the total mass of the rod. The total mass is there for a complete length L. The total mass is there for a complete length L. So think about it, for this much length, how much mass will be there? For this length, mass was m. For this length, how much mass will be there? It will be nothing but how much ever mass was there for that entire length multiplied by the length that I'm talking about. Kg per meter into meter, meter cancels, kg is remaining, which is the mass hanging below. Unitary method. For this much length, this much mass. For this much length, how much mass? For this much length, the mass is this much. So this much mass is there for this much length. So multiplied by the length itself, that will give me the mass hanging below, and that multiplied by g. So that is basically your tension, my dear students. That is basically your tension. Is this absolutely clear? This unitary method. Okay. Now what do I do? Let me consider a small cross section which is at a distance of x. So consider this particular cross section. Hmm. Now this particular cross section, like I have shown, is from the bottom side at a distance of x, and the width of it is basically dx. The width of it is dx, a small section of the rod. You are applying some force on it, because of which it elongates. because of which it is going to elongate. And let's say that the elongation is shown like this. So this is basically that elongation, that I will call it as dl. That is the elongation of that element, elongation of that particular element. And why is that come? Because of that tension, because of that tension which is there, that tension which is there, that tension has caused that particular elongation in that particular section. DL is the small elongation because the original length is also very small. Is this absolutely clear? Are you able to visualize this? Yes, very good, Siva Prasad. The question will involve integration. And you have seen this, dx term also over here. So that is also giving a hint now of integration. Correct? Very good. So now, if that is the case, I can use the definition of Young's modulus for this material, which is Young's modulus is stress by strain, stress by strain, stress by strain. Stress is force per unit area, which is tension per unit area. Okay, which is also the value of tension is nothing but mgx divided by L, and this area is as it is over here. Okay, I've just substituted the value of tension as mgx divided by L, but I have to also divide it with strain. Divided with strain. Strain is change in length per unit original length. Change in length is dl per unit original length. This is dx. Now, this is the most misunderstood term of this entire problem. Sir, wait a minute. I thought elongation per unit original length was x by L. Yes, correct. But that was for big bodies. This is a body which is a small body, elemental body. So the original length was dx. That dx extended by dl. Now every small element in that rod, dx will have different extension because the tension changes, stress changes. So every small disk will have different amounts of extension, and that's why I need integration to find the total extension of the rod, because everything will extend by different amounts. If I add every disk's or every slice's elongation, I will get the total elongation of that rod. Is this understood? Clear? Perfect. So that means I will bring dx on the top and this dl will stay as it is. Oh, let's rearrange this. Let's reshuffle this. So therefore dl will be equal to, check this out, many terms are going to be constants. Many terms are going to be constants, like m is constant, g is constant, l is constant, a is constant. Correct? What is not constant is basically x and dx. X and dx, they are not constants, they are variables. So obviously I will integrate over here, and I will also integrate over here from 0 to the complete extension, and here this will be from 0 to the complete length. This is capital L, don't confuse it with small l. This is x. X starts from here and goes till here, which is the length of the rod. This is small l, which is the total elongation of the rod. So integration of small dl will just give me L minus 0, which is again L only. So this is basically your total elongation. Total elongation. This will be equal to m. What is mass? Mass is density into volume, or rather, check this out. Okay. Length into area is nothing but volume. Length into area is nothing but volume. And let this mass remain on the top, no issues, multiplied by g. And this integration x square by 2 from the limits 0 to L. What is mass per unit volume? Mass per unit volume, that is nothing but density, correct? That is nothing but density. So in the next step, I can just write it as density multiplied by G. This will be nothing but L square divided by 2, L square divided by 2 minus 0 square by 2, which is L square by 2 only. And this on the left hand side will give me the net total elongation, the total elongation. So it is rho g L square by 2. Job is done and dusted. Is this clear, everyone? How to solve this particular question? Isn't it an amazing question which involves modulus, integration, and so many nice concepts? Very good, Krishna, Pratibha, correct. Perfecto. Okay. Great, great. And as you are watching, make sure that you are smashing that like button in case you have forgotten, and also smash that subscribe button because soon we'll be 200K, and with your help only, with your help. Okay, so 2 lakh subscribers, the #1 NEET English channel in the country. Correct. Okay. Perfect, perfect, perfect. Let's move. Let's move. Now, so we have done all these things on Young's modulus questions. So let's come back now. We had studied longitudinal stress, longitudinal strain, and the modulus of elasticity for longitudinal deformation. But remember, I have also told you there are other kinds of deformation, which is shear and bulk. So let's see the formulas for these two and start solving problems on them as well. Okay. So here we go. Starting off with shear modulus deformation, or sorry, shear deformation, shear deformation, shear deformation. Okay, so in case of shear deformation, let's say this is our surface, and okay, all right. And what happens is on the face, you are applying a parallel force. So this becomes your force. Oops, this becomes your force, which is now parallel to the surface. That surface is basically having a cross section of A. Surface is having a cross section of A. So because of which, what will happen after some time, this will bend like this over here. I hope you are able to visualize this. Yeah, just try to visualize this. It has bent slightly, and the amount by which it moves is, let's say, x. This angle which it covers is, let's say, theta. The distance between the parallel faces is, let's say, L. So L is basically distance between the parallel faces. Then your x is basically the displacement of displacement of the face, and then you have F parallel, which is the deforming force parallel to the surface, parallel to that surface which has been marked A, surface A. Okay, so all these things are given to me. So then let's start writing down one by one. Shear stress. Sigma is the symbol for stress. Shear stress will be intensity of the force, so force per unit area. That is the first formula which we are seeing. Just like perpendicular force per unit area, here it is parallel force per unit area. Next, strain symbol is epsilon, but here we are talking about shear strain. That will be the deformation relatively. So here it is measured as x by L. Now x by L, you can see opposite by adjacent in that right angle triangle. So in a right angle triangle, that trigonometric ratio opposite by adjacent is a tangent. It's a tan. So it is also tan of theta, and in most of the cases it is also roughly theta if theta is small. If theta is very small, then we know the small angle approximation, tan theta is roughly equal to theta. So this is an approximation, but let's block only the equal to formulas. Lastly, we have the modulus of elasticity, which is now called as rigidity modulus. Rigidity or basically shear modulus. Shear modulus. The symbol for that is G for rigidity. In that rigidity, that G over here, that is nothing but your shear stress divided by shear strain, divided by your shear strain. That's it. Just like Young's modulus was longitudinal stress by longitudinal strain. Check this out. We have seen this very similar looking formula over here also. Here, Young's modulus was stress by strain, but this was longitudinal strain. This was, where is it? Yeah, this was your longitudinal strain, and this stress was your longitudinal stress. Same thing, instead of longitudinal, you replace it with shear, then it will become rigidity modulus or basically shear modulus. As simple as that. Okay? Yep. This class will cover all the theory, all the formulas required from this particular chapter. Okay? MTG NCT at fingertips is good for NEET physics. Yes, Jovan, but it will not be sufficient because this year physics might be difficult. So be prepared for that. Chemistry also can be difficult. So I want you to go much beyond that. But it is essential, but it may not be sufficient. That's what I will tell you. Okay, last type of deformation, which is your bulk deformation, which is your bulk deformation, bulk deformation, bulk deformation. What is this bulk deformation? Like I said, it is usually for fluids, basically liquids and gases. So just imagine there is some gas or some liquid having some volume, let's say V naught. So V naught is the original volume of that particular fluid. What happens because of some pressure changes, the volume might change. Let's say the volume increases, for example, because the pressure has decreased, or it could be even the other way around, the volume has decreased because pressure has increased. So I'm just putting over here this particular part, and let me shade it so that you understand what exactly we are referring to. This particular part is that excess volume. So that is delta V, which is the change in the volume. Change in the volume. And why does this come? Is because the pressure has changed. So there would be some pressure on that gas or that fluid. Every liquid or a gas has some pressure. You have also seen that in kinetic theory of gases. So there was some pressure over here, and that has changed. So I'll put over here delta P, which is the change of the pressure, not the pressure itself, change in pressure. So then the stress for bulk is chumma delta P. That's all. It's just delta P, nothing else. It's not P, it's not P1, it's not P2, it's P1 minus P2, or change in the pressure basically. That's your bulk stress. If you ask me what is the strain in case of bulk, strain is the relative measurement of deformation. It is how much has your volume changed per original volume, per original volume. That is what it is. Now, actually, let's come now to bulk modulus. Bulk modulus, bulk modulus. The symbol for that is B. Now, please remember, actually, when we did this modulus of elasticity, Young's modulus or rigidity modulus, this word modulus means mod. Mod means positive, correct? Like you have mod minus 5 is 5. Mod 2 is 2. It's a positive number. So any modulus is always a positive number. Now what happens in all these expressions, stress, strain, okay, like strain can be positive, negative, because x can be positive or negative. So realistically speaking, because it is modulus of Young or Young's modulus, technically you should put a mod symbol here. But usually we do not take the negative values, so we don't use that mod symbol because we know, okay, change is this much, original is this much, so we already substitute the positive values. But technically there should have been a mod symbol over here. Same thing even in the rigidity modulus. What happens is this epsilon or the strain can be this side or this side, positive, negative. X can be positive or negative. So that is the reason why, to make this always positive, we need to ensure that there is a modulus symbol over here. There is a modulus symbol over here. Is this clear, my dear warriors? Okay. So same thing should be applicable here also. So this bulk modulus technically is the bulk stress, which is delta P, upon the bulk strain, Okay, so let me just put over here the, where is that? Bulk shear upon the bulk strain, which is epsilon bulk. Oops. Okay. And this can be positive or negative. So I'll put a mod symbol over here. That's it. So this is the formula for your bulk. But there is a very important aspect over here. Also, keep this in mind. Bulk modulus will be bulk stress. Bulk stress is change in the pressure. Bulk strain, I know is delta V by original volume, but with a mod symbol over here. Now, if I don't want this modulus, we can do one small thing over here. Observe this, guys. If I don't want this mod symbol, what I can do is I will use a logic, and the logic is as follows. See, when there is expansion, versus when there is compression, what's the difference? When you compress something, your delta P will be positive and volume change will be negative. Whereas during expansion, delta P will be negative and delta V will be positive, because volume will expand, and that comes because pressure has reduced. So that is why delta P is negative, which tells me that delta P and delta V, negative, positive, positive, negative, are always of the opposite signs, So if this is positive, this is negative, this is negative, this is positive, I know for sure. So if I always want to make it positive, if I know they are of opposite signs, just multiply it with a negative one number, it will always be positive. So that is why I will just put minus sign over here, and then rest of the things I can just put delta V by V naught. This number will always be positive. If this is negative, negative into negative, positive. If this is negative, negative by negative, again positive. Job done. Is this clear? Sahal, I definitely feel you can crack it, Sahal, because you have 1 year worth. Sorry, you're in 12th standard, my bad. Uh, See, I'm not sure that if you're in class 12, what level of preparation have you done for NEET? Is it like you are just focused on class 12, you have not studied or have no idea about NEET? Then it is definitely going to be difficult. But does not mean you should not attempt it this year, because let's say even if in the worst case you have to take a drop, worst case, you will not be starting from zero, and there is a good chance, who knows, maybe by some magic, maybe because of your hard work, and maybe the way we are teaching the preparation, things which fall into place, and what you are learning comes in the exam, you might probably get 580, 600, 620 marks, and maybe you might get some low fees private college, who knows, or maybe just happen to get a lower government college, you never know. So give it your 100%, maybe there is a chance. And let's say even if you get 550 marks, or 580 marks this year. At least you'll be starting from 550, right? For the drop year. You won't be starting from zero. Starting from zero is worse than starting from 580 or 550. Got it? Great. Yeah. Pichaku, I feel wait for 1 2 days because NTA people are mad. I don't know what they are doing. They have suddenly changed the form. So that's the reason why I made a video yesterday. I don't know whether you have seen it. NTA people have changed the form without any official notice. So let's wait for a few days. There is nothing which is going to happen if you don't submit the form in the next 1 2 days. So wait, we will see what is happening. Let NTA people declare the JA result because they are busy in that. Maybe they will suddenly come up, oh, we need that also. Oh, we need that thing also. All these things will happen. After that, we'll fill the form and I'll make a detailed video on how to fill the form. Thank you, Sahal, for all the love from Kerala. Thank you so much. And I know a lot of Malus who watch our channel. We get our channel analytics and we can see how many people are there. And thank you for all that love. Yeah, mainly our channel is supported by South Indians, and mainly we are who we are because of all the students from South India, because there was nobody making lectures for us. All the lectures were in Hindi and they were very great, no doubt about it. But we wanted to create a channel with the best teachers, with the best quality content for our students. And that's the reason why we have made this. Thank you for all the love from Tamil Nadu to Dreams. Means a lot. Yeah, you can submit it on February 20 also. Even after 10 days, you can submit it. 1 month timeline is there. Even if you submit 5 days before, no issues. But let's not submit it in March. Let's finish it by February. But wait now for 4 5 days. Don't do anything this week. Forget that the forms were released. You never know what might change. Why unnecessarily problems? Okay? All right. Fine. Yes, sir. Now let's solve problems, sir. Okay. Let's do some questions. Let's do some questions. Hmm. So what happens is, beautiful question coming up on your screen. Beautiful question. There is a rubber. This particular rubber's rigidity, rubber's rigidity modulus is, let's say, 2 into 10 to the power 6 Newton per meter square. And what happens is, there is a rough surface over here, and this particular rough surface has a coefficient of friction given by 0.5, and this has a mass. Let's say it is 40 kg. It is 40 kg. This rubber is having a mass of 40 kg, and what happens is somebody is pulling this from the top face, applying some force which is not known, but it is given to us the rubber block of side 1 meter, the rubber block of side 1 meter, okay, by 1 meter by 1 meter is pulled on a rough surface, with constant speed, with constant speed. Find the shear angle of deformation. Find the shear angle of deformation. Also, find the relative displacement of upper face with respect to lower face. With respect to lower face. So this is a question on shear modulus. They have asked the shear angle, meaning this theta, and they have also asked the relative displacement, that means x. Okay, now why is this going to get sheared? That's another story. We'll come to that. Let's start doing the question. Now, as per this particular question, let's write the solution over here. It is moved with a constant velocity. That is very, very important. So the velocity is constant. My dear students, if velocity is constant, can you tell me something about the acceleration? Can you tell me something about the acceleration? Therefore, acceleration will be how much? A big fat zero. Big fat zero. Velocity is constant. No changes. So acceleration is zero. Correct? Very good. If acceleration is zero, that means net, net force is big fat zero. Net force is zero. Oh, what are the forces, sir? See, if there is a force here, there is another force here, and that force is of friction. That force is of friction. Obviously, there is a normal like this, and of course, there is mg, which is faulty g like this. Therefore, if net force is equal to zero, therefore F will be minus F will be zero, or rather F will be equal to F, which is mu into n, which is mu mg, which is mu, which is 0.5 mass 40 multiplied by 10. 0.5 into 10 is 5. 5 fours are 20. So this will be 200 Newton. So the force is 200 Newton. This is basically your shear force, which is parallel to that surface, on the top. Is this absolutely clear? How that force is shearing it? And because of that, in the next step, I will say, that this guy, oops, this guy is going to displace like this array. My goodness. So it is going to displace like this. It's going to displace like this. And there is some displacement x over here. And there is, of course, some angle theta over here. Is this absolutely clear, my dear students, how it has moved slightly? Okay. So now in the next step, I will say that our force is 200 Newton. I already know that from our previous slide. Okay. So to find the deformation, let me use the shear concept. So shear modulus is shear stress by shear strain. Everything is shear, shear, shear. Okay. So shear stress is that force which is parallel per unit area. Shear strain is x divided by your length, or I will just put tan theta over here. That is also okay. There is nothing wrong in that. So that is basically tan theta. So that is G. So therefore, our tan theta will be F parallel divided by area. Area will be length multiplied by length. That is the area of cross section, and divided by G. G comes on the bottom. Tan theta goes on the top. Therefore, tan theta will be parallel force, which is 200 Newton. What is the length of that side? It is 1 by 1 by 1. It's a cubical box or block. So it will be 1 multiplied by 1. Rigidity modulus is 2 into 10 to the power 6, I believe. So 2 cancels, 2 zeros cancel. So it will be 1 by 10 to the power negative 4. So it will be 10 to the power 4. What has happened? Oh, what did I do? Sorry. 10 to the power plus 4. My bad. So sorry, guys. So this will be 10 to the power negative 4. And tan theta will be approximately theta only. It will be approximately theta, which is our shear angle. So this is basically our shear angle. Please remember, it is not in degree. It is going to be in radian. It is going to be in radians. Yeah, it's an extremely small angle, which is perfectly fine. Now, once I get theta, I know that x by L is also theta. Therefore, x is nothing but L multiplied by theta. Length is 1. Theta is 10 to the power negative 4. So, x is basically 10 to the power negative 4 meters, which also is x is 0.1 into 10 to the power negative 3 meters. Therefore, x is 0.1 millimeter. So, that is your relative displacement. So, that is also done. What a question. Loved it, guys. How Newton's law of friction was combined with shear and how we had to find out the angle of shear, the relative displacement of the upper face with respect to the lower face. Beautiful question, guys. Loved it. Let's go to the next question coming up on your screen. Here it is. Oh, a liquid. A liquid. Okay, one more thing, guys. I had to tell you over here. Where did that bulk modulus go? Huh. One more thing. There is one term called as compressibility. And that compressibility is 1 upon bulk modulus. Very rarely they can give you a concept on that or question on that, but that is what it is. If bulk modulus is more, means it is very difficult to compress it. So if B is more, compressibility is less. If bulk modulus is less, compressibility is more. So that is a term which is a reciprocal, inversely related to the bulk modulus. So sometimes they can just tell you, is the compressibility is more, than what will happen, or is it more compressible or less compressible? So you should understand that more modulus means difficult to compress. So more bulk modulus, difficult to compress, so less compressibility. Ability to compress is less. Is that okay? Yeah, definitely. Why not? J26 can also watch it. Why not? Okay, great. Now let's come to a question on bulk modulus. A liquid whose compressibility is 0.5 into 10 to the power minus 5. Okay, this will be meter square per Newton. It is exactly opposite in units. Has a pressure of 2 into 10 to the power 6 Newton per meter square for a volume of for a volume of 4 meter cube. Now, 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 the pressure is the pressure is 3 into 10 to the power 6 Newton per meter square. Find, because the pressure has increased, obviously the volume will decrease. Find the decrease, find the decrease in volume. That is the question. Find the decrease in that particular volume. Let's try to solve this question step by step. This is obviously a question on bulk modulus, bulk deformation, and for that we need the bulk modulus. Is that given? Not directly, but indirectly. The compressibility is given. From that I can find the bulk modulus. And we know bulk modulus is 1 by compressibility. So 1 by compressibility being 0.5 into 10 to the power negative 5. 1 by 0.5 is 2. And 10 to the power negative 5 will become 10 to the power plus 5. Units will also be inverted. So it will be now Newton per meter square. So that job is done. Bulk modulus I have found out. Great. Next, the challenge is to find out the shear, the stress for bulk and strain for bulk. From that, we can find the decrease in the volume. The bulk stress, remember, is always the change in the pressure. So, change in the pressure is 3 into 10 to the power 6 minus 2 into 10 to the power 6. 3 minus 2 is 1. So, it is 1 into 10 to the power 6 Newton per meter square. Oh, perfect. So this is the bulk stress. What about the bulk strain? The bulk strain, is nothing but how much is your volume changing upon original volume. The change in the volume is what we need to find. The original volume is nothing but given to be 4. Okay, so now it's time to substitute everything. Since we know bulk modulus will be bulk stress bulk stress by bulk strain, everything under the mod symbol. So bulk stress by bulk strain. So bulk stress is 10 to the power 6. Bulk strain is delta V by 4, everything mod. Okay. We are just trying to find the change, nothing else. Everything we are trying to find the change only. So it's all positive values. Bulk modulus is how much? 2 into 10 to the power 5. So this is 2 into 10 to the power 5 is 10 to the power 6. 4 goes on the top by delta V. Therefore, delta V will be equal to, few things will obviously cancel. This 2 with this 4 will become 2. 10 to the power 5, 6 will cancel. So delta V goes on the top. So I think I'm just getting 2 into 2 into 10. So is that change in the volume coming out to be 20 meter cube, guys? Now this is huge. Actually, the original volume was 4 meter cube. Probably because we have chosen wrong modulus of elasticity. So this should not actually be the problem's answer, because we have chosen random or wrong values of modulus. So let's make it less compressible, or let's make the original volume a little bit more or something, then it will change. Okay, so technically I should probably change, uh, let's say, let's make this 10 to the power minus 6, maybe minus 6. So then this will also become minus 6. This will become plus 6. This becomes plus 6. Okay, then it will be fine, I believe. Then this will become 2 into 10 to the power plus 6. And now when I cancel this, this will cancel. And delta V will just become 2. So 2 is fine. 2 is fine. 2 meter cube is absolutely no issues, because if the original volume was 4, I can't compress it by 20. I can compress it by 2 meter cube. So change in volume is 2 meter cube. That is perfectly fine. So I'm changing the original question. So that's how question paper designers should actually design it. So this was minus 6. Okay. If they make a wrong thing, then, gone. NTA bonus question. Awesome. Awesome, 𝐂𝐡𝐞𝐤. I'm so glad you loved my ray optics class. Somebody just told about the thermo class, and I hope this class too, it is going to be amazing. Sir, it is actually pronounced as Ibu. Who is pronounced as Ibu? Which one is Ibu? Ayo. Oh, your name. Oh my God. I was thinking which symbol. I was thinking sigma, epsilon, B, C. Okay. Which is Ibu over here? Okay. So your name is Ibu. Oh, okay. Great, great, great. Sometimes that's what happens, right? You are reading a passage, you are reading a question, and you're wondering, where is this? Where is this? And it is right there. Wow. So your name was right there. Great. Okay. Perfect. Let's do another question coming up on the bulk modulus. Now, this is also a fascinating question. Observe this carefully. If, oops, if the bulk modulus is 4 into 10 to the power 6 Newton per meter square for a liquid whose density whose density is 1000 kg per meter cube, and pressure is increased by 2 into 10 to the power 5 pascals. Find the new density. Find the new density. Let's make this 10 to the power 7 to be on the safer side. Yeah, 4 into 10 to the power 7 Newton per meter square is the bulk modulus, and density is given. If the pressure is increased, obviously it will compress, density will increase. What is the new density? This kind of questions are very common. How to do these questions? Let's see the generalistic theory, and then let's proceed to the solution. See, to solve these kind of questions, the logic is as follows. Let's assume the original, initially, what will happen? The original density will be the original mass by that original volume. Original mass by that original volume. Perfect. Okay. Now, in the new case, for that new case, after the change, after that change, what will happen? That new density, the mass will be the same, but the volume will be different. Mass will be the same, but the volume will be the different. Okay, perfect. So if I ask what is the change, if I ask what is the change, so that is delta V, which will be V minus our original volume. V minus our original volume. So, well, that will be final volume will be mass by density. Original volume was that same mass but by original density, rho naught. V is m by rho. V naught is m naught by rho naught, m naught by rho naught. So what do you see, my dear students? That the change in volume is m naught 1 by rho minus 1 by rho naught. This is going to be very useful for solving my question. This is going to be very useful for solving my question. This was the first step of the problem. Now what I will do, I'll use the definition of bulk modulus. Bulk modulus by definition is change in pressure upon change in volume by original volume but with a negative sign. I can see something over here. Maybe I'll have to use it. So therefore, delta V by V will be negative delta P by bulk modulus. What is delta V? Delta V is this whole thing over here. So let me substitute it as it is. So that was m naught original mass 1 by new density minus 1 by old density, which is rho naught. And what is rho naught? What is V? V is actually the original volume technically. So this should have been V naught. This should have been V naught. So what is V naught? As you can notice, this particular V naught which is there is over here. That V naught will be m naught by rho naught. M naught by rho naught. Is this absolutely clear, my dear students? Everybody with me? So that is your left hand side. As you can see, m naught cancels and rho naught can be taken inside. Rho naught can be taken inside. So I will get rho naught by rho minus rho naught cancels and this will become 1. Is this clear? What just happened over here? Okay, this m naught cancelled and rho naught by rho minus rho naught by rho naught, which is just going to be 1. Okay, that is the left hand side. What is happening in the right hand side? Meanwhile, I think nothing is happening. It is chilling out only. Minus delta P by B. This is also minus delta P by B. Shift that one on the other side. Shift that one on the other side. So rho naught by rho is 1 minus delta P by B. Perfect. So I want rho. Bring this guy over here. So rho will be rho naught upon 1 minus delta P by B. This is a very important formula. This is a very important formula. It's better to remember it. It is better to remember it. Is this clear, everyone? New density is old density upon 1 minus delta P by B. So if pressure increases, so this value will become 0.9, 0.8, something like that, because it is 1 minus something. So therefore, what you will get is a number which is higher than rho naught, because when you divide it by 0.9, 0.8 like that, so the ratio will become more than 1. So rho will be more than rho naught. So this is a very important derivation plus a formula which you can use. So let's use that formula over here. So the new density will be old density upon 1 minus delta P by B. The original density is already given to be 1000, so substitute it. 1 minus the change in the pressure is 2 into 10 to the power 5, I believe. And the bulk modulus is 4 into 10 to the power 7. So this will become 10 to the power 3 divided by 1 minus 2 and 4. Well, 1 by 2. This will become 10 to the power negative 2. So half is basically 0.5 and this will become 10 to the power minus 2. So this is 10 to the power 3 whole thing divided by 1 minus 5 into 10 to the power minus 3. Now, how do you do this calculation? How do I do this calculation? Can anybody put a hint in the chat box? This is going to be an extremely complex thing, but if you use some mathematical tool, it will become very easy. What is that tool? What is that tool? Thank you, 𝐂𝐡𝐞𝐤. Thank you so much. Thank you so much. Come on, come on, come on. What do you think, my dear students? 1 minus something, bring it on the top, looks like something which you have studied in basic maths. Rho will be 10 to the power 3. Write it down like this. 1 minus 5 into 10 to the power minus 3. The whole thing is raised to negative 1. This number over here is very small as compared to 1. This is that power. This is that power. And we know one thing, 1 minus x whole raised to n approximately is 1 minus nx. This is your binomial approximation. Binomial approximation. Correct, Krishna. Correct, Ibu. Correct, Pratibha. Very good. Thank you, Jovan. So let's use that. This will be, therefore, rho is equal to 10 to the power 3, 1 minus n, n is minus 1, x is 5, 10 to the power minus 3. Okay, so this will become 10 to the power 3 and 1 plus 5 into 10 to the power negative 3. Okay, so this will become opening the brackets 1000 plus 5 into 10 to the power 3 minus 3 and 10 to the power plus 3 both will come. This will just become 1. So this will become 1000 plus 5. So this will become 1005 kg per meter cube. So that's your new density, my dear students. Final answer. So that's how mathematical tools, it's a tool, it's a skill set which you learn to simplify the calculation. Loved the question, I hope. Amazing concept. Great. So these are the kind of questions that you should be expecting. All right. Now, this concept of elasticity can be also compared with springs. And I'll tell you how and where it will be useful also. So, equivalent, the concept of equivalent spring of an elastic rod. Equivalent spring of an elastic rod. What I mean is, imagine there is a rod and compare it with a spring. Compare it with a spring. This is your rod. Now somebody pulls that rod, it becomes longer. Same thing happens to the spring also. The spring will also elongate, and somebody has applied a force over here. Same thing over here, force is F. The elongation is basically X. These both are very, very comparable. The rod will have certain Young's modulus, the spring will have certain spring constant. So what is the constant of the spring which will behave exactly like the rod for the same force for the same extension? So when I say equivalent spring of the elastic rod, it is basically nothing but that spring constant. It is that spring constant which deforms the spring by the same amount as that of the rod for the same force. For the same force. And how do I do it? It's straightforward. Observe carefully. Young's modulus is stress by strain. Stress is force by area. Strain is change in length by length. Therefore, Young's modulus is FL by X into A. Rearrange it, bring X on the top, and in fact, all the things on the top except for the force. Length, you can pull it down. So, Young's modulus into area into X, and length comes below. Length is coming below. So, force is YAX by L. I have just rewritten it, manipulated it, that's all. Now, this formula looks very similar. Compare this particular formula with the formula for the spring force, which is Kx. Compare it with Kx. Immediately you will understand what we are talking about. This particular guy, Ya by L, is comparable with the spring constant. Therefore, that equivalent spring constant is nothing but Young's modulus into area divided by length. So this becomes a very important formula. This becomes a very important formula. Is this amazing? Yeah. Okay. Yeah, basically, Ibu, glass is considered now discovered lately as a very fluidic nature, but the viscosity is so high that it takes hundreds of years for that glass to flow. And this was discovered recently, where Renaissance glasses, which were colored in nature, suddenly the color started shifting down because of gravity, and it has taken hundreds of years for the colors to fall down from that glass, which says that, okay, glass is like liquid behavior, but if the time given to it is very large, but for normal time durations, you can take it for all practical purposes as solid. Is that okay? Now, coming back to some questions, or basically where it is used, specifically in SHM or oscillatory questions, where imagine you have been given there is a rod and there is a mass, and somebody gives an impulse to it, Question will be, find the oscillation, find the time period of that oscillation. Well, first thing what you will do is, this particular problem can be converted into a much simpler problem, where the rod is now replaced by a spring and this mass connected here. The spring constant being just the same formula, Ya by L. Just this equivalent spring is Ya by L. And we know a spring mass system will have oscillation whose time period is given by 2 pi under root m by k. Therefore, this will be 2 pi under root. Instead of k, you are going to put Ya by L. So this is the time period of oscillation for that particular rod. When this mass is given an impulse, it will vibrate. So the time period of oscillation is this. So direct application. Is that clear? Okay, great. Now we can also use it to find one more thing called as the elastic potential energy. Elastic potential energy. We know that an elastic body has restoring forces, and these restoring forces are conservative in nature. They are conservative in nature. Yep. Conservative forces are those forces which do faithful work without any loss. And if you go and come back to the same place, whatever positive work is done, that much negative work is done. So the total work done is zero. So they have faithfully restored it back to the original condition without causing any damage, heat loss, etc. That is the meaning of conservative forces. So elastic body has restoring forces. It comes back to its original shape and size. Hence, I can say it is conservative in nature. And a property of conservative forces is it can store the energy it can store this particular energy in potential form, in potential form, in potential energy form. So every elastic body has some elastic potential energy stored in it. So what we can do in order to find that elastic potential energy, in order to find that elastic potential energy, I have a small idea. And the idea is, why not find how much is the spring potential energy equivalent? And the spring equivalent potential energy is half K elongation square. And K value, I just told you over here, it is YA by L. It is nothing but YA by L. So why not put, instead of K, Y, Young's modulus area by length into X square. So that's it. That is your elastic potential energy. Very simple formula. You don't even have to by heart it. Just you know already spring energy is half Kx square. Instead of K, you are going to put YA by L. Isn't it very direct application, very easy way to find it? Yep, yep, correct. Now, usually, you might not use this formula. Sometimes you will. If YALX is given, sometimes you can, but sometimes you don't. Why? Because there is something else also which you need to remember. And what is that? Let's have a look at it. There is this term called as elastic potential energy density. Meaning how much elastic potential energy is stored per unit volume. And the symbol for that is rho, density, but of energy, so U. Rho U. And the unit for this, because it is energy per volume, it will be joules per meter cube. Joules per meter cube in 12th standard. You see this symbol even with electricity and magnetism. Electrical energy density is half epsilon naught electric field square, and magnetic energy density is half magnetic field square by permeability, which is mu naught. So this energy density concept is there in multiple places. It is there in multiple places: electricity, magnetism, and even in elasticity. Joules per meter cube. Okay, so how much is this going to be? Let's find that out. It is not that difficult. So rho U will be U elastic divided by the volume. Okay, perfect. So how much is the volume? The volume is area multiplied by the length. How much is the elastic potential energy? U elastic is this big thing. So half Kx square, do not forget that. So that number half is going to come. Anyways, I'll just put 1 over here. K is Ya by L, Ya by L, and then you have x square. A cancels, A cancels, and I am left with y, or rather I'll just put half first. I have y over here, I have L square, L into L square, and x square. Okay, what do I do now? Think. I want to get stress, I want to get strain. I want to get stress, I want to get strain somehow. How do I somehow get stress and how do I somehow get strain? Think about it. Young's modulus is stress by strain. Stress by strain. Okay. So instead of Young's modulus, I'll put stress by strain. And this x by L, I'll just write it like this. Wait a minute. What is this now? What is this? Stress, sorry, x by L, that is nothing but strain. So technically this is strain square. Strain cancels. So this will become half stress multiplied by strain. That is the density of the energy. This formula is very useful. Half stress into strain is the density of the energy. How dense is that energy? Amazing, right? How about we do this question again now? Which question, sir? Elephant, remember? That elephant which was there. Yes, this particular elephant question. Let's do it again, but let's do it here. Let me just shift the slides. But right now, we are going to find how much energy was involved. That's all. Okay. So we did this question. We did this question. And here we have found out the extension. We are redoing it now. We are going to redo it. But this time, what are we going to do? We will find the energy calculations. How much is that elastic energy stored in that metallic wire? Okay. Which formula do you suggest? Which formula, which formula do you suggest for finding the energy stored? Do I use this formula, half k x square, or do you think we should use energy density formula? Which one will be more easier? It's not like one is wrong or one is correct. Which one will be easier? Half k x square formula or half stress into strain formula? I don't think we need density. We just need to find the direct energy. I think half k x square formula is much better for us. So why not stick to that? Why not stick to that? So let's use basically elastic energy. This particular elastic energy will be nothing but half k is nothing but ya by L into x square. So this will be half. Young's modulus is 5 into 10 to the power 10. Area of cross section is 10 centimeter, which is -2. Square is -4. Whole thing divided by length. Length of the wire is 10 into x, which is that extension which we have found out, which was 4 millimeters. 4 into 10 to the power -3. Yes. So that was 4 into 10 to the power -3, which we have already found, whole square. Is that right? Let's see what and all things will get cancelled maybe. Let me get all the numbers first. 5 is there. 4 square is 16. And this is basically 2. And let me see now the powers of 10 alone. 10 has already got cancelled over here. 10 raised to -4, 10 raised to -10 will become +6 over here. So I am left with 10 to the power +6, and this will become 10 raised to -6. Oh, beautiful. This gets cancelled. 2 by 16 is basically 8. 8 5s are 40. So it's just 40 joules. Is that right? Just check this out. Yeah. Just check this out. Is it 40 joules, everyone? Is it coming out 40 joules, Ibu? Yes. Yes, half kx square. Perfect. Pratibha, correct, 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 correct. Oh, thank you so much. All my drawings are like that. That's why I probably had to get grace marks in drawing during my school days. Teacher felt pity at me that, my God, you are doing so well in science and what is your drawing like? So I got grace marks in drawing. But I also got to know my drawings were rids. It was like, what do you say, skibidi in the staff room. Like the drawings were circulated everywhere because they used to have fun during their breaks. So at least my drawings put a smile on many people's face in the staff room. Great. Okay. So having said that, this is 40 joules of energy which is now stored. Now I have one interesting thought in my head. I have one interesting thought in my head, although it is not asked in the question, but still it is there. Where did this energy come from? Somebody stored it, but who stored it? Nobody gives even 1 rupee for free. You have to beg to get even 1 rupee. You cannot earn anything for free, right? So same way, nobody is going to store energy without anybody doing work. Somebody losing some form of another energy. Who would have lost any form of energy? Let's think. I think gravity, because this elephant came down by some height, so there was a loss of gravitational potential energy. So there was gravitational potential energy which was lost, and that is mgh. Mass of the elephant 2000. Gravitational acceleration 10. Height by which it came down 4 into 10 to the power -3. Well, what is that? 3 zeros, 3 negative zeros gone, 4 twos are 8 and 0. So it's going to be 80 joules. So 80 joules of gravitational potential energy is lost. And that out of that 40 joules is stored. Don't you think something is fishy out here? I felt it should be 40, but it is not 40, it is 80. How is it that gravity lost 80 joules of energy, but elastic wise only 40 joules was stored? It's like Pandu was given a task. Hey Pandu, take these 80 laddus and give it to this person. And when that person was asked, hey, how many laddus did you get? He said, I got 40 laddus. Wait a minute. From my account, 80 laddus went off. I gave it to Pandu. And Pandu was asked to give the laddus to that person. But that person is saying, I got only 40 laddus. Pandu, come here. What did you do with the 40 remaining laddus? Pandu is like, sorry, Paps. I ate those laddus or I dropped those laddus. That means lost. Exactly. So, my dear friends, my dear warriors, so 40 joules of loss is there, usually in the form of heat. So, when that elephant is going to come down, the rod is going to get elongated at the expense of gravitational loss, plus there will be some heat developed in that wire. There will be some loss in that particular wire. And that calculation can also come in the NEET exam. They will give you an elephant and they will tell you how much heat was created. Students will scratch their heads. They'll be like, what, sir? What was that question? That power elephant was just hanging, sir. And you are asking me what heat loss is there? What kind of question was that? I didn't understand it. This was like some crazy skibbity problem, sir. This problem was too rich, sir. Something is sus in this problem. Where did heat come from? So the sus part or the sus part was that out of that 80 joules, 40 joules got stored, 40 joules got lost. That's how it is. Got it? Yes. That's what the problem is all about. Yeah. Yeah. Great. Okay. Now that we have done this, comes the last part of this particular chapter. And that is a beautiful concept, nothing but the curves of stress and strain. Very useful for making a choice of material. You might have heard, hey, you know what? I saw that car, but when I pressed that body, it is going inside, man. Why did they chose this? Why did they not use iron or steel? Well, you can't use iron and steel everywhere. Some parts are deliberately made soft, some parts are deliberately made hard in an automobile so that they can absorb that impact. Some mobile phones made of glass can shatter, but they give a good look. Sometimes they are made of polished aluminum because they are lightweight, sturdy, but they can bend again. You can't make an iron phone because then that would be very heavy. So the choice of materials is very important in the strength, in the structure, in the design aspect, and so many other things, the durability, etc. So these stress strain graphs is one of those graphs which engineers use to design anything. Like, say for example, you become a dental surgeon and you want to replace a teeth with another material. What kind of material should it be? Oh, it should behave exactly the same way as a human tooth. You can't get a human tooth and put it there. So you use some ceramics and some composite structures whose behavior is exactly similar as that of tooth. Their elastic properties should be similar. Their thermal properties should be similar. Their chemical compositions should be such that it does not react with the food. So many aspects are there, and one such aspect is the strength, the durability, and the elastic behavior of those particular solids or liquids. So that's why we have the stress strain graph, which gives us the analysis or the study of these materials behavior when they are loaded or unloaded. Okay, all right, so let's have a look. That is basically stress, strain graph. So now the first things is Hooke's law. And remember, Hooke's law says that stress is proportional to strain. Stress is proportional to strain, and that stress by strain is our Young's modulus. Okay, and this all happens till something called as proportional limit. Proportional limit, which means our graph initially is just a straight line, and this is a straight line till this particular point P. P stands for proportional limit. P stands for proportional limit. As you can notice, it's a straight line because it is linearly proportional. Stress by strain is constant. Number one. Number two, the slope of this graph, the slope of this graph gives me Young's modulus. So if this graph was like this, Young's modulus is less. If this graph was like this, Young's modulus is more. So the slope gives me the Young's modulus. Is that clear? What does the slope give me? It gives me the Young's modulus. Now this graph is both ways, like this and like this. What does this double arrow mark mean? So if I put the arrow mark like this, and if I put it like that, it means I'm slowly deforming it by applying more stress. So I am basically loading it. I am loading it. If I put, second, if I put an arrow mark like this, it means I am unloading it. I am unloading it. If the loading and unloading path is the same and it is coming back to the same point, that means it is behaving elastically. Because imagine if it went like that but came back over here, I started somewhere but went somewhere, so I have deformed it permanently because I have now come back via the same path and come back to the same point. That means I have come back to its original state, shape, size. That means it is behaving elastically. Elastic means it should regain back its shape and size. Okay, perfect. That is one thing. Now I decide to load it even more. I want to load it even more beyond the proportional limit. What will the behavior be? Well, it will still be elastic in nature. It will probably just go like this, maybe. As you can see, it is not a straight line, it is a curved line. And this limit is basically, I'll mark it over here. This limit is basically E. E stands for elastic limit. Elastic limit. Please understand, in that region from P to E, in that region from P to E, it is elastic. It is elastic, but what is not there? Stress. Stress is not proportional to the strain. As you can see, it is not a straight graph, so it is not proportional to the strain. So our Hooke's law, is basically invalid. Hooke's law is not valid in that particular small region, but only from this region, in this region O to P, it is valid because it is a straight line. Is this absolutely clear, my dear students? Yeah. Now the value of the stress that you get over here, the value of the stress that you get over here, it is called as yield stress. So yield stress is the maximum stress till which the body won't deform permanently. Okay, and to demonstrate that, where is it? I have a rod over here. I hope you are able to see it. I will bend it. I leave it. It comes back. I'll bend it. I leave it. It comes back. Which behavior is demonstrated by this rod? Quickly think and tell me in the chat box. Yeah. Let me know quickly in the chat box. Yeah. We'll come to that, Ebu. Hold on. That energy density and all of that. Hold on. Okay. If I bend this and leave it, what will I get? Yes, I am getting elastic behavior. Very good. Now I bend it more and I leave it, more stress, more strain, it is still coming back. But I feel now, oh my God, see, it got deformed. It has now yielded. It has now yielded. It is no longer elastic. It has deformed permanently. It has now deformed. Poor rod. I had to use it for next year batch also, not just for 2025. 2026, 2027, I need a new rod. Okay, so it has got yielded. Yes, it has gone into the plastic zone. So what happens after this is that it shows a different kind of behavior and it yields and it is going to enter plastic zone. And this will happen till this particular point M, okay, this particular point M. But the funny part is it can go this way, but it is not reversible. In fact, if you unload it, you will see that it will probably come back over here. If you unload it from here, it will probably come back over here like this. What is this telling me? What is this point? Very interesting point. Stress is zero, but the strain is there. That means it has been deformed without any force. This means it has now got permanently deformed. Permanent deformation, or it has been permanently set. It has been set. It has been set into a new shape. And this particular zone from E to M, E to M, this particular zone is then called as plastic zone or plastic behavior. This is called as plastic zone or plastic behavior. Is this absolutely clear? Why it is plastic in nature? Yeah. Awesome. Oh, you're 2026 only. Okay, great. Okay. Yes. So when it crosses E, it is behaving plastic in nature, just like I showed you for this rod. For small deformations, elastic, elastic, elastic. Plastic, see, deformed, permanently set, permanent deformation, no force. I'm not touching it, but force is not there, but it has gone set permanently. But if I bend it, I don't want to bend it so much, but visualize and you bend it so much, it breaks. That will happen after M, and suddenly you will see it will fracture over here. This is irreversible, you can't come back. And this M is the maximum loading point. This M over here is that max load, maximum load, and finally it fractures. It fractures. There is no point in drawing the graph after this point because it has broken now. It's no longer a proper solid. It has fractured completely. And you cannot come back over here. Once you enter this zone, that's it. You are gone forever. Okay, once you cross M, that's it. It is irreversible. It's gone forever. You have to break. No doubt about it. And the funny part is the graph is coming down, which means the stress is decreasing, yet the strain is increasing in that zone. So when it breaks, when the process of breaking happens, when it is breaking, okay, you will see in that zone from M to F, the stress is reducing, but the strain, the deformation is still there. That is what is very interesting. Even if I'm removing the stress, still it's like, no boss, you did the damage, I am not coming back. It's like a relationship. This graph is like a relationship. Okay, imagine Pandu and Champa loving each other. Pandu gives love, Champa also gives love. Pandu fights, Champa also gets angry. Pandu fights, their strain develops. Pandu is causing a lot of stress on Champa. Champa is also getting strained. Pandu is giving stress, Champa is getting strained. Linearly proportional till a point. Then it becomes non-linear. Little bit Pandu tells, hey, why are you doing this? Champa gets even more angry. What is this every time you come? But then Pandu is like, sorry, 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 sorry. So they come back. They come back to their original shape. They are elastic. So Pandu fights with Champa. Again, Pandu says sorry, unloading. They come back to their original lovey-dovey relationship. Then what happens? One day, Pandu fights too much. Champa, what is this? What are you doing? You have no shame in this. They fight a lot. And Pandu is like, sorry, 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 sorry. My bad, my mistake, my mistake. But damage is done, permanently set. Deformation happened. Full deformation happened. Gone. They have gone into the plastic zone. Another day, Pandu becomes even more angry. I don't know what is wrong with this Pandu. Pandu, hey, what are you doing, Champa? In front of everyone is cold. That day, the limit, maximum loading point of Champa was reached. Done. Sorry, Pandu, I'm done. And she walks away. Champa walks away. And Pandu again runs behind her. Hey, Champa, please, please come back. He's trying to remove the stress, but the strain is still increasing. Champa is like, get lost. I am going. This is done. Irreversible. And the breakup happens. Fracture happens. Got it? Understood? Is this absolutely clear? I'm studying 12th grade. I want to give NEET this year, coming June 7th only and 17. I think it should be not be a problem, Rajkumar. Just check the birth of date and the eligibility criteria. I don't think it should be an issue. Just check once. Okay, great. So this is what happens. And yeah, that was it. Now, there is one more thing over here. And I need to mention that. Where is it? If at all I measure the area under this graph, the area under stress versus strain graph. What will it be? It's the area of a triangle, right? Half stress into strain. Half height, which is stress, base, which is strain. Oh, wait a minute. Half base into height. This is just that. Correct? Half base multiplied by height. That's what I have done. This I know. What is this? I have done this just some time back. Where did it go? Half stress into strain, energy density. Exactly. So basically, what it gives me is nothing but the elastic energy density, elastic potential energy density. So the area under the graph exactly gives me that. Area under the graph exactly gives me that. Now, this also means one more thing. If I am loading and unloading, then what does this area give me? What does this particular area give me, which is area enclosed? I am going and coming back. This particular area, my dear students, this particular area of that loading and unloading, this is also called hysteresis. Hysteresis means your going and coming path is not the same. That is the hysteresis. It is also there in magnetism. When you magnetize and demagnetize, the paths are not the same. You go to the school via one road, but come back via some another road. That's like a hysteresis loop. Hysteresis loop. Hysteresis loss, also there in transformers. Remember that hysteresis loss, because when you magnetize it during the positive cycle, demagnetize it, again magnetize it. So you're doing things again and again, but reversing it in direction, but not via the same route, not via the same path. Then there is some loss which is happening. There is some thing which you are giving up. So there is some loss which is there. That area of that hysteresis gives me the loss of energy per unit volume. Loss of energy per unit volume. That is also very, very important. Is this absolutely clear? Yes. The energy loss per unit volume, many people just write it as loss of energy. Be careful if there is an option which says loss of energy and another option which says loss of energy per unit volume. loss energy per unit volume is the right answer. Okay, always density is what you get. Always it is the density is what you get. Got it? Clear, everyone? Awesome, awesome. So that is your stress strain graph. There could be a simple question on the area or on the slope, or is this elastic behavior, plastic behavior, some simple things. We'll be doing questions, of course, in the problem practice sessions. But for today, this particular session is done and dusted. The concept of Young's modulus elasticity will also come in thermal physics, where you have thermal stress developed under a rod. And just to give you the formula, I'm just writing it here, but in thermal physics lecture, you can see it. So thermal stress concept will come. Thermal stress of a rod, which is given by Young's modulus, coefficient of thermal expansion and change in temperature. Young's modulus, coefficient of thermal expansion and delta T. That's also the place where it comes. It also comes in sound, velocity of sound. Velocity of sound also you will see Young's modulus will come, and that formula is just given by in solids. In solids, it is nothing but Young's modulus by density. You will also see velocity of sound in liquids. In liquids is nothing but bulk modulus by density. You will also see it in thermodynamics. In thermodynamics, there is a concept. Thermodynamics also you will see this particular concept where the thermodynamics and it relates with fluids both together, thermodynamics and fluids, where the bulk modulus is the pressure. Bulk modulus is the pressure if the process is isothermal. If the process is isothermal, and the bulk modulus is gamma times the pressure if the process is adiabatic in nature. So many places you are seeing the concept of modulus of elasticity, different chapters. And of course, SHM also, I just showed it to you over here. Where did it go? Time period of oscillation. This was also one of the beautiful application of Young's modulus in oscillation chapter, where you convert it into a spring. Yeah. Now, somebody is asking, sir, what is this elastomer graph and all of that? See, I'll tell you one thing. Imagine somebody gives you a graph of stress versus strain like this, and I tell you the graph is something like this: straight, thoda non-linear, then there is this point, and then what happens is there is this plastic zone over here, and then it breaks, and then it breaks, okay, over here. Now compare it with this particular graph over here. Again, it is stress versus strain, okay, and that graph again very similar like this, but this is like this, and then it breaks over here. If you ask me, compare the properties of the material, compare the properties of the material, I would say this particular material has very small plastic zone. So this kind of material is definitely more brittle, brittle like glass or ceramic, glass or ceramic cups or ceramic plates. Brittle means they break when you apply more force. See, why that is like this is because if you go into the plastic zone, then you get an idea that it is going to break now. When I was bending the rod, if I see that it is not coming back, then I have an idea. I get a hint. I get a warning that wait a minute, this material is about to break. But when the plastic zone is very small, there is a very less chance that I will enter that plastic zone. Immediately, I will reach the maximum loading point and it will break forever. So that is why when you have a small plastic zone, then you will see the material is going to be more brittle. Is this absolutely clear? Okay. Now, there are materials which have a very large plastic zone. Imagine a material like this. like this, and very large, extremely large plastic zone before it finally breaks. When they have a very large plastic zone, very large plastic zone, such a material is then called as an elastomer. Elastomer. The value of strain can be very high for such materials, like 1,000, 2,000, 10,000, meaning the original size was 1 centimeter, but you can keep stretching it, stretching it to 1 kilometer also. So many elastomers, many these nylons and these fibers are drawn from such elastomers, where they take a small piece, they heat it, and they are drawing it into long wires by stretching it. So such materials are then called as elastomers. Is that absolutely clear? Absolutely clear? Very good. Another thing which you should be aware of is that sometimes they can ask you, I have these two kinds of graphs where I load it, it goes like that, but while unloading, it comes like this. I load it, it goes like that, and while unloading, it comes like this. As you can notice, the area enclosed is different in both the cases. Here it is less. Here, obviously, it is higher. Obviously, it is higher. So, what can be the application of each kind of rubber? Both of them are rubber. Example, both of them are rubbers of two different types. What is the difference in them? If the area is less, that means the heat loss is definitely going to be less. Here, there will be heat loss which is more. Heat loss is definitely going to be more. So, this kind of rubber is usually used for shock absorbing. For shock absorbing purposes. Because imagine there is a machine which is vibrating, tug, 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 tug. You want to absorb the shock. So you place it on such a rubber, loading, unloading, dug, 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 loading, unloading, loading, unloading. What will happen? All that energy will be absorbed and lost as heat. So you're absorbing it really well. This won't be able to do it. But this rubber should be used for manufacturing tires of a car. Why? Because when the tires rotate, it will be pressed, again decompressed, pressed, again decompressed. The same piece of rubber will go on the top, unloaded, loaded, unloaded, loaded. In this process, if heat is developed, the tire will become hot. The air inside will become very hot and the tire may burst, which is not desirable. It can cause accident. So that is the reason why this kind of rubber is usually used for manufacturing of tires, so that you can prevent heat and you can also prevent the losses. Is this understood, my dear warriors? Absolutely. Okay. So this is how the understanding of the stress strain curves come from. Elastomers, brittle nature, okay, heat losses, and also the usefulness of modulus of elasticity in different chapters. Cool. Great, great, great. So we have completed this. We have not left anything in this chapter. We'll be doing more problems during the problem solving sessions, of course. Okay, but the concepts, I'm pretty sure it will be done. So if you have understood everything well, please let me know in the comments that yes, sir, done. This solids is done, or you can just write a comment saying solidified. Yeah, you can just put a comment saying solidified. Yeah, I would understand that then you have watched the class till the end and you have understood everything as well. Thank you so much for liking. Please share this channel with all your friends. Let's make this 200K quickly. Yeah, smash the like button and subscribe. Let's go 200K very soon. Bye bye. Take care. Have a great time. Lovely evening as well. Bye bye.